In the summer of 1912, commercial apiaries across the northeastern United States were recording an outcome that challenged the prevailing logic of honey production. Colonies managed with 8 frames in a standard 10-frame super were consistently outperforming colonies running at full 10-frame capacity, not by a small margin, and not in isolated cases. The pattern appeared repeatedly across multiple yards and multiple seasons. The bees were not doing less, they were storing more efficiently, fewer frames, more honey. Have you seen anything like this in your own colonies? A super that seemed slower to start, yet capped out before others. If you've kept bees long enough, you may have noticed it without understanding why it happened. What you were seeing was not an accident. It was the result of a single measurable variable, frame spacing, and its effect on how a colony builds, ripens, and stores honey. If this kind of biological precision matters to your management, consider subscribing. This channel covers colony mechanics at the level that actually affects yield. What most beekeepers misunderstand is this: the number of frames in a super does not determine the amount of honey a colony can store. The depth of the comb does, and comb depth is controlled, to a significant degree, by how much lateral space the bees have to build into. This is not a marginal adjustment, it is a structural one, rooted in how colonies regulate their own space and how that regulation responds to measurement changes as small as 6 millimeters. The standard Langstroth super, in common commercial use by 1912, was designed to accommodate 10 frames at a center-to-center spacing of approximately 35 millimeters. This spacing produces comb of a standard depth, functional, predictable, adequate, but commercial operators who removed 2 frames from that same box, spacing the remaining 8 frames at approximately 42 to 44 millimeters center to center, observed something that would eventually be documented by some of the most respected names in early 20th century apiculture. The bees built thicker comb, deeper cells, and those deeper cells held significantly more honey per frame than standard-spaced comb. The total volume of honey stored per super increased, despite fewer frames being present. To understand why this happens, it is necessary to understand how honeybees regulate their own comb construction. Bees do not build comb to a fixed depth because of a biological program that specifies a particular cell length. They build comb to a depth that responds to available space, colony strength, and nectar flow intensity. When frames are spaced at the standard 35 millimeters, the bees build to the available depth and stop because the adjacent frame limits lateral expansion, and the bee space between combs, approximately 9 to 9.5 millimeters. The critical passage width first formally described by Lorenzo Langstroth in 1851 is already met. When frames are spaced wider, when the gap between adjacent combs increases, the bees do not simply leave that space empty. A colony under active nectar flow will extend comb into that available space. The cells grow longer, the honeycomb itself becomes thicker. A standard frame running 10-frame spacing typically produces comb with a finished depth of approximately 28 to 32 millimeters on each face. Under 8-frame spacing in the same box, that same frame, built out by a strong colony during peak flow, can reach 38 to 45 millimeters per face. That is not a trivial difference. Consider what this means volumetrically. A standard 10-frame super with comb built at 30 millimeters per face holds a certain quantity of honey across its combined surface area. An 8-frame super with comb built to 42 millimeters per face holds substantially more honey per frame, and the total box volume, measured in extracted weight, can exceed the 10-frame configuration by a meaningful margin. This is not theoretical. It is geometry applied to bee behavior. More frames does not mean more honey. More comb volume does. And comb volume responds to spacing. There is a second mechanism operating simultaneously, one that commercial beekeepers in the 1910s identified through yield records before it was formally articulated in apicultural literature. Honey ripening is a process of water evaporation. Bees reduce the moisture content of nectar from approximately 70 to 80% at collection to below 18 to 20% at capping, the threshold at which honey is stable and will not ferment. This evaporation process requires airflow through the cell, fanning activity, and time. It is one of the primary rate-limiting factors in honey production during a strong nectar flow. Thicker comb, the kind produced under wider frame spacing, does not alter the chemistry of ripening, but it does change the structural geometry of how bees manage the process. With deeper cells and wider interframe passages, airflow through the super improves. Fanning bees have more effective passage space. The colony's evaporation capacity, its ability to reduce nectar moisture toward capping threshold, is modestly but measurably supported. The practical result: colonies operating under wider frame spacing during a strong flow tend to cap honey at a more consistent rate than colonies operating at standard spacing. In a short nectar flow, which is the reality for most temperate climate beekeepers, faster capping means more extractable honey before the flow ends. Faster capping, denser comb, more honey per box. The mechanism is simple. The timing of when you apply it is not. This is where the practice breaks down for most beekeepers who encounter it, and why the results reported by early commercial operators were so inconsistent when the technique was adopted without understanding the conditions that made it work. Frame spacing adjustment in honey supers is not a universal modification. It is a flow-dependent one. Applied incorrectly, either too early, too late, or to a colony that lacks the population to exploit the available space, it produces no benefit. In some configurations, it actively delays production. The biological requirement is a colony that has already reached foraging saturation, a population large enough that every available frame in the super is being actively worked. Under 8-frame spacing, the surface area available to the colony is reduced compared to 10-frame spacing. If the colony does not have the workforce to cover that reduced surface area with intensity, the thicker comb potential is never realized. The bees simply do not build into the wider space quickly enough to benefit from the flow. The commercial operators of the 1912 era who documented this technique were running colonies with overwintered populations, strong spring buildup, and supers placed at or just before peak nectar flow. Their colonies had typically reached a strength of 12 to 16 frames of bees before supers were added, a threshold that ensured the foraging force was large enough to exploit reduced frame count without any loss of working density. Colony strength threshold for 8-frame spacing: a minimum of 10 to 12 frames of bees covered with workers, an active queen with a stable laying pattern, and a brood nest that has already begun to expand into its second brood box. Anything below this threshold is not a candidate for reduced frame count. The timing of super placement relative to nectar flow onset is equally critical. Supers placed too early, before the primary nectar flow has begun, allow bees to begin drawing comb in cool, low-flow conditions. The result is irregular, shallow comb that does not benefit from the wider spacing, because the biological stimulus for deep construction active nectar intake under population pressure is not yet present. Supers placed too late, after the main flow has already peaked, result in comb that begins construction after the highest intensity nectar availability has passed. Comb depth is still achieved, but the window for maximum nectar intake is shortened. The correct placement window: when the primary nectar source in your region is within 7 to 14 days of peak bloom, colony strength meets the threshold above, and daytime temperatures are consistently above 18-64 VSEF, the minimum at which bees will build comb productively in upper boxes without clustering below. Managing 8-frame supers requires a modified inspection protocol compared to standard 10-frame management. Because comb builds thicker under wider spacing, the visual cues that experienced beekeepers use to judge super progress, the rate at which white wax appears on frame tops, the proportion of cells showing nectar intake, remain valid, but the timeline is compressed. In a 10-frame super under standard spacing, a strong colony typically shows full frame coverage and significant nectar intake within 5 to 7 days of super placement during a strong flow. In an 8-frame super under wider spacing, that same colony will show heavier per-frame loading earlier, but the overall super will not appear as uniformly full as a 10-frame configuration at the same stage. This difference misleads beekeepers who are accustomed to reading progress by visual fill. Inspection interval for 8-frame supers during peak flow: every 5 to 7 days. Look specifically for comb depth on the outer frames. If outer frames, frames 1 and 8, are not being drawn within 7 days of super placement, the colony has not reached sufficient strength to fully exploit the configuration. Consider adding a 9th frame temporarily to reduce spacing until population increases. Do not assess super progress by lifting corner frames alone. The most accurate assessment of comb depth requires removing a center frame and observing actual cell length, not just surface coverage. When comb on center frames has reached approximately 35 mm depth on each face and shows active nectar intake in the lower 2/3 of cells, the colony is building correctly under wider spacing. If comb depth on center frames is below 28 mm at the 10-day mark under active flow conditions, the spacing is likely too wide for the current population. Add a second super when the first is approximately 60 to 70% capped. Do not wait for full capping. Waiting compresses the bees into finished comb, reducing available cells for incoming nectar and initiating backfilling in the brood nest, a condition that accelerates swarm pressure and disrupts the queen's laying space at the exact moment when the colony should be directing all energy towards storage. Backfilling is not a storage surplus. It is a warning signal. Most beekeepers who attempt frame spacing reduction make the same sequence of errors. Understanding this sequence is as important as understanding the technique itself. The first mistake happens before the season. A beekeeper reads about reduced frame count in honey supers from a historical source, a beekeeping publication, or a conversation with an experienced keeper, and decides to apply it uniformly. 8 frames in every super, on every colony, across the entire yard. They remove the frames, set the spacing, and wait for results. The result, in most cases, is underwhelming. Colonies below the strength threshold do not build into the wider space. Comb is drawn slowly, unevenly, and often with burr comb in the gap between outer frames and box walls, as the bees attempt to close what they interpret as an abnormal void in the hive structure. This produces frustration, not honey. The second mistake is timing. Supers are added on the beekeeper's calendar, not the colony's biological calendar. Frame spacing reduction offers no advantage if the colony is not already in a state of active nectar processing under high foraging intensity. A colony receiving 8 frame spacing before the nectar flow has begun is simply a colony with less available comb surface during the build-up period. That is a liability, not an advantage. The third mistake is colony selection. 8 frame spacing benefits strong colonies. It does not benefit average ones. A beekeeper who applies this technique uniformly across a mixed-strength yard will see measurable improvement in their strongest colonies and no improvement, or mild production delay, in colonies running below threshold. They conclude the method failed. The method did not fail. The preconditions were not met. The intervention window is narrow. Once the primary nectar flow has ended, once the main bloom has compressed and passed, there is no recovery. The honey was not stored. The season is closed. For a small producer depending on that yield for income, a misapplied technique is not an abstract error. It is a specific number of kilograms not extracted, not sold, not recovered. The mistake happened weeks earlier. For beekeepers managing between 5 and 50 colonies, the nectar flow is not a background event. It is the primary income window of the year. A flowering period that lasts 14 to 21 days, the typical primary flow window for most temperate regions, represents the entirety of the honey harvest for that season. Efficiency at the frame level is not an academic exercise in those conditions. Every frame that stored 280 grams of honey instead of 400 grams because the comb was built shallow at standard spacing represents a measurable production loss. Multiply that across 8 frames. Multiply it across a super, multiply it across 10 colonies, multiply it across a short season with 1 primary bloom. The frame spacing adjustment documented in commercial apiary records from 1912 onward was not adopted as a curiosity by historical operators. It was adopted because it produced measurable results under the specific conditions that commercial beekeepers were already managing. Strong colonies, precise flow timing, and supers placed at peak colony strength. Those conditions are replicable today. The biology has not changed. The flowers have not changed. The mechanism that drives bees to build deeper comb under wider spacing is identical now as it was in 1912. The nectar flow still compresses into a narrow window. The colony still responds to space and pressure. The comb still builds to the depth the bees determine is warranted. What changes is whether the beekeeper applies the technique correctly or whether they apply it as a general modification, watch it underperform in mixed-strength conditions, and conclude it failed. The center-to-center frame spacing in a standard 10-frame Langstroth Super is 35 mm. 8-frame spacing in the same box produces a center-to-center distance of approximately 42 to 44 mm, depending on box interior dimensions and frame ear width. That is a difference of 7 to 9 mm, less than a centimeter. A measurement a beekeeper can set with a simple wooden spacer cut to specification, a modified frame rest, or commercially available frame spacers designed for exactly this adjustment. The tool is not complex. The measurement is not difficult. What is difficult, what commercial beekeepers in 1912 understood, and what the yield records of that period confirm, is that the measurement only produces its intended result when applied to the right colony, at the right stage of the season, within the correct temperature range, under active nectar flow conditions. Applied correctly, comb builds thicker. Honey volume per frame increases. Capping progresses consistently. The super fills to a higher extractable weight. Applied incorrectly, irregular comb, burr construction between frames and walls, delayed filling, and no measurable gain. The spacing is one measurement. The conditions are the mechanism. The timing decides. Commercial apiarists in the early 20th century were not working from biological mystery. They were working from observation, repetition, and careful record-keeping. The same tools available to any serious beekeeper today. The frame spacing adjustment documented in 1912 apiary records was not a trick. It was a structural modification to honey super management, grounded in how bees build comb in response to space and nectar flow. It produced consistent results when applied to colonies that met the strength threshold. Within the correct seasonal window, under active flow conditions, it still produces those results today. The biology has not changed. The bees respond to the same pressures. The measurement is still 7 to 9 mm. The timing still decides.